for now, I'll just get started. So let's begin with a word of prayer. I think it's time to start, right? 11:15?
Yeah.
Okay, so I'll start. Dear Heavenly Father, we thank you for this day. We thank you for this wonderful room and its delightful chilliness. I just pray that you'd guide our steps today, help us to glorify you again, Lord, in what we do. And we just pray that we'd learn a little bit more about differential equations and how they work and so forth. In your name I pray, Lord Jesus. Amen. Okay, so we talked about the three main methods of the first order differential equation last time. You know, separation of variables, integrating factor, exact equations. And what I'm talking about now is just a little bit more on the problem of exact equations, all right? So like here's a good example to get us started. We're supposed to find the solutions of 2x y squared dx plus 2x squared y minus sine of y dy, right? So the idea, if it's exact, right, we're looking for, what are we looking to do? Well, I guess I have it up here, I don't need to write anything, but we're trying to find some f, right? The differential of f is exactly this again, right? So what that means is I need this to be partial f, partial x, right? And I need that to be partial f, partial y. So I'm trying to solve partial f, partial x equals this, and partial f, partial y equals that. Does this look at all familiar to you guys? I don't know how long ago you had Calc 3. Remember when we had a vector field, if we could find a potential function for it? This is exactly the same calculation, right? Like you try to integrate with respect to x, you try to integrate with respect to y, mix and match, try to see if any... What? Come on. That's my computer, and it's being stingy with its battery. Well, that'll happen again, but it's okay. All right, so the point is to basically integrate this with respect to x, right? Integrate that with respect to y, sort of partial integrations. So this integrates to x squared y squared. This integrates to x squared y squared plus the cosine of y, right? And so obviously we got x squared and y squared on both of them. And so you get the solution x squared y squared plus cosine y just basically by integrating both of these separately. Does that make sense? I mean, I haven't written it all out here, but that's what we did in Calculus 3. I think maybe here do I do it a little bit more? Let's see, here's another example. You've got x dx plus y dy over x squared plus y squared equal to 0. We're hoping that this is an exact equation. So basically here I'm just like, if I look at 1/2 natural log of x squared plus y squared, the question is, where did this come from, right? Well, fine, but it actually just comes from integrating either this or that, right? If you look at what we're trying to get is the partial derivative of f with respect to x being this, partial derivative of f with respect to y being that, which I'm reading from the original differential equation, right? I'm sorry, I'm probably off the screen for the video. I have trouble doing more than one thing at once. All right, so, this, of course, differentiates to give both of these things like you like. So what's that mean? That means that the solution to this differential equation is given by 1/2 log of x squared plus y squared equals to k. All right. If you want to, you could exponentiate this, and you get something like the square root of x squared plus y squared equals e to the k. So it's a circle of radius e to the k. Kind of weird, right? By the way, I mean this. Oh, what? Hey, that's a typo. What am I missing here? What did I mean to write there? Right? So this right here, I'm saying that this equation and that equation have the same set of solutions, right? So I meant to put the dx and the dy there like that, right? That's what I was intending there. Again, those are almost the same differential equation, except what's the difference? Well, the one that we're looking at in this example, 2.3.6, can you put x and y both 0? No can do. Got division by 0, right? But this one, of course you can. Although this is not a differential equation. Sorry. You know what I mean. The one that I was supposed to write there, okay? So Yay, my cameraman's here. Let's see here. So, oh, you haven't missed much. All right, so there's obviously a connection between conservative vector fields and exact equations, right? You notice that the calculation, the determining of the level function is essentially the same as the problem we had to find the potential energy function, right? Remember this problem? Basically, you got a vector field f, m, n, and the question is this equal to the gradient, right, of some other little function f, or you could say some phi, right? So that's tantamount to solving partial phi, partial x equals to m, and partial phi, partial y equals to n, right? And then we said that phi was the potential function, right, in calculus 3. It's almost the same animal here that we're trying to do, right? So there's a natural connection between the conservative vector field and the corresponding exact equation, right? In fact, if this is a conservative vector field, then m dx plus n dy is in fact an exact equation. Here's a little calculation that's kind of neat. If you want, you can pick 2 points, x naught and, oh man, I wish I had a picture of this in here. Let me see if I can. Let's see here. So here's the picture. I'm glad you're here, Luke. Otherwise, I'd have to keep running back there. So here's the picture, basically. Actually, this isn't the right picture. Why not? What do I say here? Let's see. Where is it? Let's see here. Well, I said let C be the level curve of f, which starts at x naught, y naught, right? The tangent vector field of the level curve f is perpendicular to the gradient vector field along C. It follows that, so let's see, try to express that here. So suppose we're looking at, just to give you guys context here, let me start at the beginning. So we're considering the differential equation. It's an exact equation, m dx plus n dy equals to 0. We want to find solution through x naught, y naught, all right? And so what we're looking for basically is the function, right? So the function fxy equals to a constant. This is going to be, describes the solution set, right? So we can also graph that, right? So just heuristically, suppose the graph looks like, oh man, contrast of purple on purple, not so great. So this is, suppose it's the level curve, right? What's the relation between, first of all, what's the gradient of f? If this is the solution, so the level function which solves this exact equation, that means that partial f partial x is m, and partial f partial y is n, right? So the gradient vector field corresponding to level function is exactly the vector field mn. Do you guys remember geometrically what's the relation between the level curve and the gradient to the level curve? Perpendicular, great. Yay. It warms my heart to hear those words coming from a student's mouth. All right, let's see here. So yes, it's perpendicular. Because there are some semesters in differential equations where I ask that question and I get nothing but awkward silence for 2 minutes. Thank you for saving me from that. So this is the gradient vector field. It's perpendicular. Of course, the gradient vector field tells you the direction you need to go to level up, right? It points in the direction of leveling up in the f curves. So what's that say then? You can see geometrically then the deal. What's the integral of f dot dr going to be equal to? Along this curve C. See, geometrically, dr is like this, right? It's the tangent, infinitesimal tangent vector, right? You guys are mostly engineers. I'm allowed to see these sorts of heuristic things, right? At f dot dr is 0. You add up 0 across an interval, it's still 0. I mean, this is clearly 0, right? But on the other hand, this is what? In differential notation, it's m dx plus n dy, right? So this gives us like a pretty sweet identity to derive solutions. I'll show you how it works. So basically I say, but we have path independence, right? So rather than looking at the solution curve, we can also do what? We can take like a horizontal curve, right? This is x naught, y naught, and suppose x1, y1 is, oh, I did that already, right? So you can take the, let me erase this here. So you could just do this, right? You can go like that, right? In other words, y equals to y naught, x equals to t, and over here this curve is what? X equals to x1, y equals to t, for t from what? Like that. And how do I know that the line integral along this horizontal line segment and that vertical line segment are the same? Well, it's a conservative vector field, right? It has path independence. And when you actually work out the details of that, that gives us let's see here, the horizontal line segment does what? It only picks up the m piece, right? And the vertical line segment only picks, m as in mummy. And this one, n as in nanu nanu. Oh, I'm sorry. Is that too dated? No one knows what nanu nanu is anymore. It's Mork and Mindy. The late, great Robin Williams. Anyway, so my point is, when you work out this calculation, it just leaves you this and that. And this is like a stone-cold formula. And then, of course, what you do is, instead of taking x1 and y1, you just leave it as x and y. And this gives us a formula for the solution to an exact equation in terms of a line integral. So here you go. Suppose you have a differential equation which is exact on a simply connected region U. The simple connectedness is necessary so that we don't get hung up on any, like if there was a hole here, then we couldn't deform this curve to that curve. It would have been a problem. But that's not allowed in a simply connected region. So we have this, though. Integral from x naught to x of this, integral from y naught to y of that, equal to 0. That is the equation which solves the exact equation, and also contains x naught and y naught as a point on the curve. So here's a proof that it's right. What do I do? Oh, again, this is in the thing I posted. It's page 23 in Blackboard. Sorry, in the notes that I posted. So I'm a glutton for punishment, so I took the differential of that just to check that I was right, you know. And fundamental theorem of calculus, and I got it. So, excuse me. I had to meet in the middle, though. So I think I had to. Oh no, this is the differential of the m piece, and this is the differential of the n piece. When you add them together, they cancel. So, all right. Anyway, that's not so. I showed you an argument for it already. I don't need to show you two arguments. I probably won't even test you on this in all likelihood. It's just something I wanted to show you because I think it's neat. But here's an example of how to apply this dreadful beast. It's actually not a dreadful beast. There are other things that we should call dreadful beasts. This is not one of them. Sorry, I digress. So here, this exact equation, 2x, y, where'd my laser go? Ah, yes. So this is an exact equation. You can check. How do we check? You guys tell me. We take the partial derivative of this with respect to what? The x part, you differentiate with respect to y, right? Is that equal to the derivative of the y coefficient with respect to x? If those are equal, it's exact, right? That's the case here. This differentiated with respect to y gives me 2x plus e to the y. This differentiated with respect to x gives me 2x plus e to the y. They match. So I can use the theorem I just explained the derivation of to you. And when you do these integrals, so like I have to take m and evaluate it x equal to t and y equals to y. So that gives me 2ty plus e to the y, right? I take n, I plug in 0 for x, I plug in t for y. So that gives me 2t plus e to the t. You do these integrals, and there you go. That because I'm looking, I want to find the solution through the origin.
Oh, okay.
Right. But that was just a choice to illustrate the theorem. Here, another example. Same theorem. You can, this one, remember we solved this guy last time? Remember? The circle? We solved this 2 different ways last class. Here's how to solve it with this silly theorem. If you want the solution through the point x naught, y naught, I just feed this m and this n into the theorem, evaluate it at the appropriate, that's supposed to be y naught, right? No, wait a minute. Oh, man. I think this is a cut and paste error. I'm supposed to have what here? This should be y naught, right? Or is that supposed to be, this is definitely supposed to be x naught. That's supposed to be x. Oh man, there's a typo here. This is right, but, and I think this is right. In retrospect, that is supposed to be x naught, right? And I believe that's supposed to be y naught, but that won't actually hurt us. I'm not sure. I have to go back to the proposition. Anyway, I've already spent entirely too long talking about this, so I'm gonna move along. Interesting application of this, of course, is the physically significant. These could be the components of an electric field in 2 dimensions, right? Then if you look at E equal to minus the gradient of V, then V is the voltage. So as you think about solving an exact equation, the level solution, those could give you equipotentials, curves of equal voltage, whereas the significance of the coefficients of the differential equations is that they're the x and y components of the electric field that you're looking at. So that's one physical application for you electrical engineers. But, all right. Tell you what, let me put this away and just ask you guys, do you have any questions about anything in particular before I move along here and continue on? Oh man, I just did that, didn't I? There was one other thing I was going to show you. You should be happy I show you this. It is a lot like one of your homework problems, I believe. Didn't I ask you a homework problem like this? I tried to print your homework out today, but my printer is a little sketchy. I need to. Well, I bought some new cartridges, but they're not here yet, obviously. So yeah, here's your homework, right? So what's the best way to avoid failing this class? It's pretty simple. Like, do the homework. Do a little bit of homework every day is the best answer, all right? If you try to do it all the day before it's due, it's not going to work for you. I mean, this sort of thing, you have to kind of let marinate a little bit, you know? So you try it and you get stuck, you try again. Send me an email if you get stuck on a particular thing, you know, I'll help you. So here's a differential equation which is not exact. Lovely. And I say solve this ODE by the integrating factor method. And then I give you a template for the integrating factor. This is the kind of question I might ask you on the test. I won't ask you, okay, so there's like only one integrating factor I expect you guys just to know. That's the linear, that's the dy dx plus py equals to q, the one we looked at in depth last time. Other integrating, like exotic integrating factors, I will sort of give you a template, and then maybe you have to do some differentiation in algebra to figure out. This is such a problem, right? I give you a template, but you still have to know what to do with it too, right? How do you solve the differential equation? You multiply it by the integrating factor, right? And then you're able to find the level function, which f equals to a constant is the solution. So that's what you got to do here, right? Now, there's an example in the notes, much the same, which is what I was pointing out here. This guy, example 2.3.12. See, here's a wonderful exact, well, not exact equation. It's not exact. It's inexact. But if you try multiplying it by x to the a, y to the b, you'll be able to make it exact. So what do? Multiply this by x to the a, y to the b. I use laws of algebra, right? So like, when I multiply x to the a times 3x, what's that do? It gives me 3x to the a plus 1. And then there's a y to the b, that nothing happens here, right? On the other hand, this one, I've got 2x to the a, y to the b minus 1, because it's 1 over y, and so forth, right? And so I just multiply x to the a, y to the b in here and distribute, use my laws of exponents and so forth, algebra basically, and then I apply the exactness condition, right? Partial y partial m is equal to partial x partial y, partial x partial n, and that gives me this equation. But the only way these two can be equal is if they have matching coefficients for like powers. Are there any like powers here? This guy and that guy, right? That tells me that 3b has to be equal to a plus 2. On the other hand, I've got x to the a, y to the b minus 2. Is there any similar term over here? Nope. That means that 2 times b minus 1 has to be 0 by polynomial algebra, basically. You maybe never did any algebra like this before, that's why I'm showing you. All right? So anyway, that gives you b equals to 1 and a equals to 1, which tells us that xy is going to be an integrating factor. So I go back up here, I multiply by xy, it gives me this thing, at which point I can figure out my level function, x cubed y plus x squared. That function, right, has a differential, which gives me back this. Consequently, solutions to this differential equation are simply x cubed y plus x squared equals to a constant. Now, I multiplied by an integrating factor, x times y. I might have lost what? Solutions, right? I could have lost the x identically equal to 0 solution or the y identically equal to 0 solution. In other words, the x and y axes could have possibly have been solutions to the given differential equation. Now, y equals to 0 is not a solution to the original differential equation because it's not defined there. And x equal to 0 arguably is a solution, but it's a little bit dicey too because the origin you got to throw out anyway. So, but a little nuanced, but you know. The main thing here, of course, is finding everything. Getting the extraneous solutions right or commenting on them, of course, is the icing on the cake. So, oh, here is a fun example that I will put away here. I just mention it briefly. If you look at this, of course, what is this? This is the standard dy dx plus py equals to q problem we did last time, right? If you maybe, oh, is this what you were going to tell me about, Luke? So. Oh, that's funny. I mean, yeah, this is, I said I had no explanation. That's not entirely accurate. I mean, this is sort of an explanation for why the integrating factor is what it is. So if you look for an integrating factor, right, just multiply this by I. That gets us to IPy minus q dx plus I dy equal to 0. For this to be exact, we need the partial derivative of this with respect to x is equal to partial derivative of that with respect to y. Right? And then I assume for the sake of discovery that I is just a function of x. If I do that, then we get to ip equals to di dx, so that gives us di over I is equal to p dx. You integrate both sides, and that gives you I as the exponential of the integral of p dx. So you found that to be a satisfying explanation for why the integrating factor is what it is? Yeah. I guess so, but there's still this kind of like sketchy. I mean, it's not exactly that sketchy. It's like, well, why do you need to do that? But like I said, for the sake of discovery, I guess what I'm thinking is maybe for some engineers, the thing that you guys would like to see is something like the physical significance of the integrating factor. Like, what is the physical significance of the integrating factor? There has to be some kind of physical significance as it relates to, you know, some problem you're interested in, RLC circuits, or maybe an RL circuit, or a QC tank, or something. I don't know. Whatever it is that excites you guys, I don't know. Oh, this theorem is just a point of trivia. Let me skip it. And that brings us to substitutions, all right, which I'd like to just kind of do without this. That's why I was putting this away. Yes, I am sure. It's like, are you sure? Yes, I'm sure. It doesn't trust me. It's like, are you sure? I'm starting to idiot-proof these things, huh?
Yeah.
Yeah,
Last time you put it like more chairs.
that's true.
Maybe it hurt.
But it didn't ask me last time.
Maybe it hurt.
Oh, that's kind of scary.
Someone's watching this classroom.
So what's your major?
Industrial systems.
Industrial systems, you? Mechanical? Mechanical? Computer engineering? Industrial systems and electrical. All right. So sorry, I'm mostly talking to Luke. No, there are some mechanical engineering. Industrial systems, I don't know what you guys do. It's a mystery to me. Well, probably this compartmental analysis stuff is important. But, all right. So, there's more to say about the connection between exact equations and Green's theorems and stuff, but I think I've said enough in here for you guys. If you want to talk to me more about it in office hours, I'm happy to. There's more in my Calc 3 notes, I know, but certainly I think we've said enough for our purposes here. Let's see here if I can't find a nice equation to start us with. How about this? dy dx, all right, equals to x plus y minus 6 quantity squared. So what we're doing now is broadly under the topic of substitutions. When we finally get our books, this will probably be section 2.6. I'm not sure. I'm currently looking at the 4th edition of the book. I have the 3rd. I've got the 4th. I will soon have many copies of the 6th edition, as you will. I bought 10 copies of it. So statistically speaking, there's a pretty good chance that we'll have 7 copies in the next 2 weeks, at which point you guys will have a book. And I think I'm going to ask you guys for $5 for it. That's okay. I think that might still leave us with almost enough money for a pizza party, so it's a pretty good deal. Yeah. Yeah, the 7th edition is where they start costing some money. But, I mean, okay. So how would you solve this? First of all, the techniques we already know, they don't work. I'll just save us the time. All right? You could FOIL this out. Maybe that would make one of them work. I don't know. But I don't want to do that. Here's what you do. This is a problem for a substitution. What would you make the... So what should our substitution be? How about this? We call this thing, right, V. So what we're going to do is let V equal to x minus y plus 6. I think that's what we do. I had this dumb memory of the board project the screen. I had this dream that the screen came down over here and it left me that whole board to work on. But I realized that it was, I guess math is the only people who actually use these boards like they ought to be used. Everybody else just scribbles like nothing that matters. I don't know. Apparently most professors, I don't know. I'm not sure if most professors don't care, but this is, it's entirely too big for this room, for one thing. And I'm sorry, I'll just stop talking about it. All right, so dy, so this is my substitute, my new variable. And check it out. So what's dv dx equal to? 1, right? Minus dy dx. So what does this tell us then? Put this all together, make the substitution. What do we have? We have dy dx, right, is equal to What is it equal to? It's equal to, yeah, 1 minus dv dx, right? But what else is it equal to? What's this up here? V squared, right? At which point we're like, hooray, because this is a much nicer differential equation in terms of v and x, which we probably can solve. So then what we're going to do is what we always do. So this gives me dv dx equals to what? 1 minus v squared, right? Huh. Yeah. Oh, but I got a v squared there, yeah? Not quite then. There's a typo in the notes here. Man, who wrote these notes? I want a refund. Let's see here. Now, how could we make that minus become a plus? Okay, so how would that happen? That would happen from putting a plus up here, right? Okay, so let's do that. I'll make the corrections. So let's make that a plus, this a plus, all right? This a plus. That makes this a plus. No, that's not what that does. That makes this dv dx minus 1, right? Then that gives us dv dx equals v squared plus 1. That's important because otherwise I'd have to talk about hyperbolic tangent or hyperbolic cotangent inverse as integrals, or we'd have to do partial fractions, which you guys could do, but I just was trying to keep this example relatively simple. So let's make this modification. So no, I can't do the integrating factor method. This is a nonlinear problem. But I can separate variables and integrate, and that gives me inverse tangent of x is equal to x plus a constant. Not x, right? What was this? V, right? And then what does this give us? Inverse tangent of x plus y plus 6 is equal to x plus c. And so finally, well, that's fine as a implicit solution, right? There's an implicit solution. To get an explicit solution, what do? I take the tangent of both sides, right? So I get x plus y plus 6 equals to the tangent of x plus c. And if I want, I can solve for y. Y is equal to minus x minus 6 plus the tangent of x plus c. And there you have it. That is the solution, the explicit solution to the differential equation. I don't know about you, but if I look at dy dx equals to x plus y plus 6 squared, I do not expect to find a tangent of x plus c as part of my solution. I don't know. I love differential equations. The problems you can solve just basically with algebra and calculus you already know. It's really fantastic. But so the comment I was going to make you guys is for the one that's actually in the notes, if I had dv over 1 minus v squared, the integral of that, right? You got two different ways you can go. The one is that that's the inverse hyperbolic tangent of v plus a constant, and that's only good for the absolute value of v less than 1. Or you can use the inverse coth for v greater than 1. Or you can do this. Let me check the sign on that. Other way around. Might still be wrong. So partial fractions here. I guess it should be plus. See, because then I get 1 plus v here, 1 minus v here, 2 cancels, and I'm left with the product in the, yeah, okay. So like another way, the integral of dv over 1 minus v squared would be 1/2 the natural log of the absolute value of 1 minus v plus the natural log of the absolute value of 1 plus v. And I suspect that that formula reduces to both of the formulas above in the appropriate domains. Anyway, that's why I wanted to change the sign. Okay? Otherwise, to do the integral in the notes correctly, we'd need to know these things, which you may or may not know at the moment. But there's a reminder in case it comes up later in the course, okay? Various methods we look at involve integration, right? And anytime you do integration, it's a dangerous thing, right? All right, so continuing with our story of substitution. So do you see the basic idea here, though? Setting aside, I mean, integration's always scary because it's kind of open-ended, right? But basically, just the idea here, the concept of this example is what? If we have dy dx equals to some function of something like ax plus by plus c, right? Then a v equals to ax plus by plus c substitution is probably helpful. Okay. A next example. This is an example of what's called a homogeneous equation. But it's not, I mean, we use homogeneous equation a couple different ways in this course, and this is a dissimilar use. The predominant way we use homogeneous is the way I talked about last time, right? Like, there's no forcing function. So this is a different use of the term. But here it is. Y over x plus 1, y over x minus 1. Right, so here's a second example. I guess I should call this example 1. All right, you guys. So what do you think we're going to make our substitution here? What should we make v? V equals to what? We have a winner. So v equals to y over x. Now I want you guys to figure out for me, while I'm drinking my soup, what's the relation between dv dx and dy dx? And what does this differential equation become when we change it to v and x rather than y and x? So your goal is to replace y and its derivative in terms of v and its derivative. And you'll forgive me for drinking this soup. That's hot. But this soup is the reason I'm not coughing today, so it's in all of our interests. Luke, is the jibber jabber still jibber jabbering the audio bar?
It is.
Jibber jabber jibber jabber. Okay, very good. I'm not sure about the battery life of these. I got a new mic system that's works on AAA's, you know. The Amazon review said 3 hours, but I'm on my 4th hour, so I don't know. I personally like to multiply both sides by x before I do anything. So that gives me like v plus x dv dx equals dy dx, right? And that's equal to v plus 1 over v minus 1, which gets me to where I want to go the fastest, which is that x dv dx is equal to v plus 1 over v minus 1 minus v. it doesn't really matter how you do the algebra. If you do it correctly, you'll eventually get yourself to the same differential equation I get to. Whether or not you do this, I mean, if you differentiate this directly, what would this give us? It gives us dv dx, right? Equals to 1 over x dy dx, right? Minus y over x squared. But then if you go down that path, you kind of have to get rid of this y here and replace it with a v. So how do you do that? Y equals xv, right? If you multiply that by x, you get back to my identity down here that I have here. Here. Right, this is the same as this if you just multiply by x, right? The point is you got to do the product rule. If you don't do the product rule, you'll be wrong. So then what? How do you deal with that? I would suggest making a common denominator, right? So this is what? V plus 1 minus v times v minus 1 over v minus 1, otherwise known as what? 2, right? Plus v minus v squared, yeah? Over v minus 1. That's all equal to, I'll write it again over here just for our convenience, dv times x over dx. Now we can separate variables, right? So let's do that. What's that give us? That gives us dx over x on the one side. Well, that's easy. But on the other side, we got what? V minus 1 dv divided by what? Tell you what, let me make that a 1 minus v, because I don't like working with minus v squared. So I'm going to absorb the minus into the denominator. So, goodness gracious, 1 minus v over v squared minus v minus 2. So I just multiply that by minus 1, right? So then we integrate both sides, right? So how do you integrate that? Oh man. Seriously? Oh, I think I've done something wrong. Oh, yes, I have. You guys should have stopped me here. This is why we can't have nice things. Yes. Rewinding. Here, this is not a 1, right? 1 doesn't cancel the 1. This is a v. V plus v is 2v. So we get 2v plus 1, right, minus v squared. So that gives us dx over dx equals the integral of, I was about to say, that this integral looks harder than I remembered. V minus 1 dx over, oh, dx, listen to me, dv divided by, let's see here, minus v squared plus 2v plus 1. So you let w equal to, you know, v squared minus 2v plus 1, and then dw is what? So if you like, we can, let me go ahead and absorb the minus upstairs again. There we go. In other words, the dw is what? It's 2 times yeah, 2 times v minus 1 dw. So there's a sign, right? I think we have a minus, integral of minus the integral of dw over w. So I get minus the natural log of the absolute value of w plus a constant, which is minus the natural log of the absolute value of v squared minus 2v minus 1 plus a constant. And of course, all of that's equal to what? It's equal to the natural log of the absolute value of x. So what can you do? You can absorb the minus into here if you want, right? Take this minus, make it a minus 1 up here, right? And this plus, you know, natural log of plus a constant, how can you absorb that into a log? We'll take the exponential of both sides, right? What do we get? 1 over the absolute value of v squared minus 2v minus 1 equals basically a constant, e to the c. I'm gonna bring the constant to the other side if it's okay with you guys. So that gives me e to the c absolute value of x. And then this is what? Remember what v was? I guess I could just write this as what? This is really e to the minus c times is equal to absolute value of x times the absolute value of v squared minus 2v minus 1, which is what? Yeah. Yeah, we got to put the y over x back in. So this is y squared over x squared, right? And this is minus 2 y over x minus 1. So if I multiply the x in, that gives me absolute value of y squared over x minus 2y minus x, I believe. I guess technically I should have absolute values of x there, though. Oh, sorry, am I behind the stupid monitor? Yeah.
Where we differentiated w, w equals b squared minus 2b minus 1. Next line is dw equals 2b minus 2 dw.
Oh, that's a dv. Thank you. Because I substitute that over here. And oh, and that's why I'm missing a half too, aren't I? Ah. I'm sorry, guys. Let me just just forget all this. It's not entirely, I mean, it was under the right spirit of things, but it wasn't quite right. All right, so this, we got to be careful. This is a half, there's a 2 here, right? So when I make this substitution, there's a half. It's minus a half, right? And so there's a minus a half here. There's a minus a half here. Plus a constant. Now that's equal to the natural log of the absolute value of x. And let me just skip the details, but basically algebra gets you to y squared minus 2xy minus x squared equals to k. Again, just basically algebra and plug in v equals to y over x. If you're not already good at algebra, these problems will help you fix that. Well, if it doesn't kill you first, I don't know. It's my own stupid fault for hurrying. Don't hurry. You just make more work for yourself with these kind of problems. So there you go. That's the solution. Something like that. Now this is called, again, this is called, basically, if you have dy dx is equal to something like some function of y over x, this is so-called homogeneous problem. I'll put that in quotes. Problem a v equals to y over x substitution might be helpful. Right? It was here. Let's look at another problem. Now, substitutions, some semesters I downplay this more than others. But I think it's a good thing to look at substitution. The nice thing about these problems, right, is that on the one hand, they give you a little bit more practice with differentiation and substitution. But the other thing is they also sort of give you another chance to try to learn the basic 3 techniques, because all these substitution things always come back to either an exact equation, separation of variables problem, or on occasion linear ODE. So here's our next problem, and this is actually part of a large class of such problems called Bernoulli problems. Do you guys know who the Bernoullis were? I mean, I don't think you know them. They've been dead for a while, but there are like 3 of them that did a bunch of pretty important stuff, more or less around the time of Newton, give or take 100 years. So you're close enough. So here's the problem: y prime plus xy equals to xy cubed. Y prime plus xy is equal to xy cubed. How are we going to solve this? So let me call this original equation. Let me give it a name. Per my usual name calling, we'll call this thing star. I think this will be our last substitution example for today. There's a few additional methods beyond this, I think, but I think this one will suffice. Let me see here if I got much more to do past this. There's a linear substitution, and there's also a substitution in terms of like polar coordinates. But I think what I'll do is I'll use the projector again to do those. I'm going to work through this one though, because I think you should see it work through. All right.